This is a brief introduction to Sector Lisp. Sector Lisp is a Lisp that fits in less than 512 bytes, a disk sector. And here's the URL for it. Here are some of the parts of Sector Lisp. We'll look at memory, we'll look at conn cells, strings, and how memory is allocated. Memory in the code is called M, capital M. It can be thought of as an array of conn cells. Each conn cell has a char and a coulter, 2 slots. In this version of Sector Lisp, conn cells are kept on essentially what is a stack, a set of pointers that grow away from 0 in one or the other direction. The word cons originally came from the word construct. Strings are kept in memory. They also use conn cells. The char of each cell contains 1 character in this version. In other versions of Lisp, there may be 2 or more characters, whatever fits in a char. And the coulter points or is the index of the next conn cell in memory. The last character in a string also sits in a conn cell, just the way every other character does. And that coulter points to 0 or nothing, to nil. And that's how the string is terminated. Memory is allocated in 2 spaces, a conn cell space and atoms. That's where we also put strings in atom space. Both of them grow away from 0, one to the left, one to the right, or up and down, however you want to call it. There is no heap per se. Sector Lisp works on a scheme of stack-based allocation. There are no cycles in the lists, and that results in no defragmentation. What can we learn from studying something small like Sector Lisp and stripped down? Well, first, we learned that 8-bit byte addresses are more efficient space-wise than 16-bit addresses, and those are more efficient than 32-bit addresses, and those are more efficient than 64-bit addresses. What we also learn is that a very minimal functional programming language can be fitted into 512 bytes. One of the conclusions is that we could split development up into 2 portions. One is the actual invention and development of a program using the best workstation we have, and then production engineering it later in 8 or 16 bits or something smaller for running. Furthermore, we learn that byte codes are based on 8-bit bytes for a reason, and the reason is smallness. Further to the idea of splitting development up into 2 parts, one could use parsing expression grammars, PEG, I favor old JS, to write SCN, which is solution-centric notation, which really is just a mini DSL, but it's targeted at exactly one problem instead of a class of problems. One can write the program in a language, parse it using PEG, and then put a different back end on to get better efficiency later. That splits you up into 2 languages, a development language and a production engineering language. We'll look at this minimal Lisp to start with. We'll look at it in 3 parts. A function as a list, function formals and body, how to get them out of a list, and then the 6 basic functions that make up this small Lisp, which was based on McCarthy's Lisp 1.5. A function is a list of 3 items. The first item is the keyword lambda. The second item is a list that contains the formal parameters, which are basically variable names. And then the third part is the body of the function. If we have a function as a list, then we can extract parts of the function using standard Lisp terminology. For example, this part, the formals, can be pulled out by taking the coulter of f, which is this thing, and then taking the char of it, which is that. To get at the body, we just do more of the same. We get the coulter of f, the coulter of that, which the first coulter is this, the second coulter is that. Then we take the char of it and we get the body. The six basic functions are eval, apply, evcon, which does conditionals, evlist, which evaluates a list of things, assoc, which is a table lookup, pair list, which takes two lists, a list of names and a list of values, and then joins them together into separate concells, each concell containing a name and a value, and then takes that list of concells and jams it onto the front end of or the environment. The environment is really just a table that maps names to values. In the original Lisp 1.5, it was formed as an A-list, which had a list of pairs, and each pair had a name, dot, and a value, and the dot really just means that this part is in the car and this part is in the quitter. If the value is actually nil, it prints slightly differently. That's just a short form for printing things in the list. The first two functions to look at are eval and apply. They're the real workhorse of all of this stuff. They call the rest of these other functions. Eval basically takes the expression, returns its value within the environment as given. Eval will call apply whenever it hits a lambda or an anonymous function, and it'll call that function on the expression. Con and evlist are helper functions to eval and apply. Evcon basically evaluates a conditional. It takes a list of condition expressions dotted with the actual body of the code. The first condition expression that defines that's not nil, then it evaluates the body and returns. So if it found that that was nil, found that that was not nil, something other than 0, then it will call eval on that body. Evlist evaluates a list by taking the first item in the list, evaluating it, and then quittering down the rest of the list and evaluating each item in the list. Assoc is just a lookup function. It looks up a name in the mapping table. Pair list is used to make up the mapping table. It'll take a set of two lists and tack each name in list 1 to the value in list 2. Keep doing that, and then when it's finally done, it tacks all that stuff onto the environment. And because all of this stuff is done functionally, the environment gets passed in as a parameter. Tacking things onto the front is very inexpensive and is functional, that when you return from a function, you go back to having the environment that you had when you entered the function. Eval handles a couple of things as special forms. It cases off for quote or for con and handles them directly. We'll see that later. Apply handles 5 built-in functions. You might also consider those to be special forms, and it handles anonymous lambdas. The 5 built-in functions are EQ, cons, atom, car, and quitter, and everything else is assumed to be some sort of anonymous function that looks like a list, as we've seen before. It has a 3-element list, a lambda, a set of parameters, and a body. Lambda itself does not appear explicitly in the code, but it appears as the final else case of the case statement that makes up the body of apply. If the function being passed in is a list, which means it's less than 0 in this particular code, then apply binds the arguments and tries to call eval on that function. Begin looking at a very simple example, how the list quote space A is stored and evaluated. Here we're looking at memory for the first example as a linear array of bytes, and every pair of bytes forms a concell. The positive ones store first the string NIL. The quitters point to the next cells, and the final quitter points to 0. And so that's how nil and quote are stored. Then we have a bunch of characters coming in. The reader routine, which I won't take apart, reads this list into negative memory, -2 and -4, leaving nil, quote, and lambda. Well, that's for the next example. We need A. A will be read into memory also, and it will form a small list of 2 items. The list starts here. It says it points at +6. +6 is quote, and then -4 is the quarter, and that cell points at +30 in the car and nil in the quarter. +30 is where we've stored the letter A, or the string A. And that is roughly how that code will store things in memory. For the simple example, we're going to call eval with -2, which is the pointer to the first con cell of the list, quote A. And the environment in this case is nothing, nil. Eval handles quote directly, and it'll return the car with quarter of -2, which is +30, and that's the item A. And that's the end of the example. There's not much more to it. The second example is slightly more complicated. It starts with a list of 2 things. The first thing is an anonymous lambda, and the second thing is an argument of quote A that will go into the lambda. Second example code is here with the characters, and then the reader reads them into memory. To put them into memory, to draw out the memory, I had to do this in 2 steps. The first step was to try and draw the example in a nested form and then flatten it out later. There's actually a mistake on this diagram. This pointer here should actually be pointed here. The top level is actually a list of 2 con cells. The first should be a list that contains 3 items, and the second thing should be a list that contains 2 items, a quote method A, and I've got them backwards here. So the list that contains 3 items is here, the list that contains 2 items is here. The second item in this list here is a list of X, and so that points to another set of con cells, and here I think I've got a +32, which is the actual X. And I put a list around it, which is that con cell, and then we'll cell. And we can try to follow the evaluation of this second example. I only did a few parts and then gave up because drawing it up was just too hard. It first calls eval with -16 and 0. That executes this line of code and then returns on apply, evlist, and so on, and the stack at this point is essentially empty. We bookmark this evlist, then call evlist, and there's a bookmark placed on the bookmark stack. And here, and then we keep going like this until we hit nils and the evlist stops. It pops the stack back. We come back to here, and we try to do an eval. We need to push another bookmark of C onto the stack and so on, then I gave up. This can be followed by examining code in more detail.